I don't have any announcements really today. You're all, I think, cracking away on the homework, and we will continue on. All right, so we are talking about this very fundamental subject in quantum mechanics, which really came to the fore in the context of quantum optics, but it's of course a fundamental subject more broadly in quantum mechanics itself. And that is this whole idea of a quasi-probability distribution. And we're talking about this in the context of quantum optics, where we're looking at representations for in phase space, where the phase space corresponds to the quadratures of a mode of the function. Okay? And so what we have is that we can express any expectation value of any operator as an average over phase space in terms of representations of the state and representations of the operator. Okay? So these are phase space representations of the state and the phase space representation of the operator. They come in this duality where sigma corresponds to the operator ordering index. Okay, so they come in this duality. And we can obtain this sigma ordered representation of the state through this formal expression as a trace inner product projecting rho onto the operator ordered delta function, which replaces the operator A with the complex value alpha and the operator A dagger with the complex value alpha star, with all this heavy-handed formalism that we have, what this thing means. Okay, yeah?
So that ordering for the delta function?
Yeah.
What would that look like if you were to try to write it out? Like, is it just like...
So let's do an example as we saw. Let's say I had this, if this were the case of, say we wanted to calculate this, for example, for sigma equals +1, okay? So that would be, we wanted the normally ordered guy here, okay? So that would mean what in this case? Well, that's that. In this case, we had to do it with the +1, right? So we have this duality. So what does this operator actually look like in that case? I'm sorry, this guy's +1, so I got to do it with the -1. Excuse me, I didn't remember which one I was doing. So what's that one? What's that one?
Just erase your brackets, I guess.
So that is anti-normally ordered, which means all the A's are on the left and all the A daggers are on the right. So what does this delta function look like in that case?
Can I do a Fourier transform?
I could do that. I could go through all that stuff, go through the Fourier transform. But in that case, that's just equal to this. Because we've done it. All the A's are on the left and all the A daggers are on the right. And if I were to do this sigma equals -1, then it's that. And if it's 0, what is it? Well, then we don't have an easy way to write it down. But for the case where sigma is 0, then this thing, the symmetrically ordered guy, is the Fourier transform of the displacement operator. the Fourier transform of the symmetric plane wave. Is a symmetric delta function. Now, in your homework, you have these quite annoying problems of having to calculate these things for a whole variety of states and do a whole bunch of nasty Gaussian integrals and so forth, which, you know, will scar you for life. You know, you kind of see what goes into the tasks of calculating these things. So, I mean, and we'll come back to this in a moment, how, as examples of actually doing a calculation, right? Right now it's a kind of formal expression. How you actually go about the algebra to do it. We'll look at an example or two, or at least one. All right. So, right. So, you know, in certain cases, as we said, as we've shown, you know, there are simpler, this thing reduces to a simpler expression in certain cases. So the Husimi distribution is, in some sense, the easiest thing to calculate. You just have to calculate the matrix element, the diagonal matrix element of the density operator with respect to a coherent state. So if you can calculate this expectation value, that's the Husimi distribution with this normalization here, okay? And typically when people want to calculate in a quick and dirty way what the phase space representation is, you'll calculate the Husimi distribution because it gives you some of the coarse features. We'll understand what I mean by coarse in a moment, okay? Why this is coarser than other representations. But it's an easy thing to calculate, and often that's what we do if we want to just get a little flavor of things. Wigner wrote down this expression, which is a, you know, phase space distribution. That's again something we can in principle calculate. You see, this is related to Fourier transforms. It's a kind of expression of this sort, buried in there. They're equivalent. Okay. And you know, the Glauber. So yeah, this of course is the Husimi. This is the Wigner function, and this is the Glauber Sudarshan P representation. I'm not giving you an expression for the P here. I'm just saying that rho is, in the P representation, looks like a statistical mixture of coherent states. That's why Glauber wrote this down originally. But of course, if the state is non-classical in the Glauber sense, then this is not an honest-to-God probability distribution. It's a quasi-probability distribution. And typically, as we'll see in a moment, it's actually a highly singular function. It doesn't really exist as it's just a formal expression. Okay. And one of the ways we saw that is looking at this formal object, which is an object that appears in statistics. In statistics, we call the characteristic function the Fourier transform of the probability distribution. In quantum statistics, we call the characteristic function the Fourier transform of the quasi-probability distribution. Okay? So that's the Fourier transform expressed in this 2D way on phase space, which is equivalently the expected value of the plane wave, right? The Fourier transform of a probability distribution is the expected value of the e to the I kx, right? And then we have this factor here relative to the operator ordering. Okay? Now, the characteristic function is also a useful mathematical tool because it is the generating function of moments. So if I take the derivatives of this at this origin of phase space, I find out what the nth order derivatives are related to the nth order moments. Okay? So it's something that's used quite often for that kind of calculation. From a formal perspective, this is also useful in helping us to understand a little bit more about the relationships between these different quasi-probability distributions. So, we were talking last time about the question about existence, whether these functions are good functions, whether they exist or not, and we have a little bit of formalism here, talking about so-called bounded operators, ones that have a norm that is finite, where we're talking about the trace norm of the operators. And that trace norm, if I'm talking about a Hermitian operator, is just the square of the symmetric representation. And that's always going to be true for the density operator. If I looked at perhaps I should say this particularly, I think it'd be easier to talk about this in the case of the density operator. So this is the trace of rho squared. And that's always finite. Okay? And that can be expressed in terms of this square normalization. I'm not sure if I got the factors of pi right. I'm sorry, I can't remember. Look at it. But key point here is that this is square normalizable, which means that this exists. The Fourier transform. If the Fourier transform is square normalizable, then you do the inverse, you get a well-defined function, right? That's a Fourier theorem. So this is a well-defined function. But if I look at, for example, for the Q function, the corresponding characteristic function here, in this case, well, that is this, as follows from this, right? This is the Wigner function, characteristic function. Right? So this guy is even more square normalizable, so the Q function always exists. But the P function, which is related to the anti-normally ordered representation, has this blowing up exponential. So this thing is not always guaranteed to be square normalizable. So the P function may not exist. And that is to say, for the states that are non-classical, there isn't even a good P representation for it. Only for the states that we call classical light in the Glauber sense can we even write down a good P representation. So these relationships here of how these different orderings, how these characteristic functions are related with these Gaussian factors, right? This is just a Gaussian in phase space, centered at the origin, right? Means I could do the inverse Fourier transform, and I can think about relationships between the different quasi-probability distributions, right? So For example, I can look at, so let's look at the relationships. Between these guys. So the Wigner function is the inverse Fourier transform of the characteristic function. Right? The characteristic function is the Fourier transform of the Wigner function, inverse Fourier transform. I get back the Wigner function. But the characteristic function with symmetric order is related to the characteristic function with normal order, or vice versa, right? So, for example, I can look at the Q function is the inverse Fourier transform of the normally ordered characteristic function. But that is the inverse Fourier transform of the Gaussian factor times the normally ordered guy. Right, that's what we just said over there. So, I ask you, if I want to take the Fourier transform of the product of two functions, or the inverse Fourier transform, how do I do it? Convolution. The convolution, right? So this is the convolution of the Wigner function with the inverse Fourier transform of the Gaussian. So when you put in all the factors, and this I'm pretty sure is correct, I get an integral So, what does that tell you about the relationship between the Q function and the Wigner function? Well, this is a kind of smearing out, right? I'm looking at every point in the Wigner function and I'm multiplying it by a Gaussian. And that Gaussian kind of smears out the resolution, right, of whatever fine structure might be in here is now smeared out. And that's what happens. As you know, this is always positive. The Husimi function is always positive. Whereas the Wigner function can be negative, and that negativity is washed out by that smearing function. The same thing is true. The Wigner function is a smeared version of the P function. So whereas the P function might not exist, this should be squared, pardon me, these are Gaussians. Whereas the P function might not exist, this smeared version of it always will. And this is, then the Q function is super smeared with an even wider Gaussian relative to the P function. Where so this thing falls, falls off faster, this is a more, even a wider Gaussian. So they're all smeared versions of one another. Okay? With, in some sense, the P function the most fine-grained, so fine-grained that it can't even capture the uncertainty principle and blows up. The Wigner function, the Goldilocks of all quasi-probability distributions, always exists but can be negative. The Q function, the Papa Bear, totally overdoes it and is always positive and doesn't capture any of the non-classicality in the system. So let's do a very quick and easy example.
Should they all be d squared alpha prime or?
Yeah. Picky. All right, so let's say I have a coherent state. Okay, so my density operator is a pure state. So, question, what is the P representation of this state? It's a delta function. We don't have to do any calculation, just look at it, because we have over here, this is what we have is the general relationship here. So if the P, this guy is just a delta function at that value of alpha naught. What is the Wigner function?
Gaussian?
So how would you get it? How would you calculate that?
Convolution.
We could use, this is easy, this is a quick and dirty way here, because we know the relationship here. If we have the P function, then we can quickly calculate the Wigner function through this kind of but if you were on a desert island and you didn't have that formula with you, you may not have remembered that one. But on a desert island, you certainly remember the formula, generally speaking, for how you calculate quasi-probability distributions. How would you calculate, just in a general approach, what would you do if you wanted to calculate the quasi-probability distribution? What you would do, almost always, especially for Gaussian-like states, is you calculate the characteristic function first. You do that because you can do that, and then you can do it, and then you can use the way in which you know how to take Fourier transforms of Gaussians, right? So the characteristic function of this guy in symmetric order is what? Well, that is equal to the expected value of the displacement operator. And that you can calculate, right? And then you take the inverse Fourier transform and you get that. Okay. What about the Q function? Again, lots of different ways to go about it. I'll just say, if I didn't, have this formula here, it's always easy to calculate this, or easy-ish on the ish side. In this case, it's quite easy, because this is equal to, alpha is and this we remember is beta. So what do those things look like? Well, let me rewrite this guy over here. I'm going to write W, the Wigner function, as a function of x and p normalized over dx dp as 1/2 that, which is 1 over pi e to the minus x minus x naught squared e to the minus p naught squared, which is equal to 1 over the square root of 2 pi delta x squared e to the minus x minus x naught over 2 delta x squared and then a similar one for p where delta x squared equals delta p squared is a half. So what is that? That's a two-dimensional Gaussian where there is a variance in x that's equal to the variance in p, which is equal to a half. So, and similarly, for the q, we have a Gaussian which has the same form. I'll call it, for normal ordering, got the same kind of form that we have with the p, but delta x plus 1 squared is 1. It's twice as big. It's more smeared out. So what do these things look like? Well, the p function is a delta function. Can't even draw it. It's a point in phase space. Okay. What about the Wigner function? Well, it's centered at this point, and it has, if I look at it as a function of x and p, so I'll just leave it in x and p, then it's centered here, and it has, it's a Gaussian. It's a Gaussian that is centered on here. And when we draw this dashed line here, what we're drawing is a contour of the Wigner function, which represents, say, the 1 over e point, right? Or the variance. So this thing has variance here, or RMS, 1 over root 2 in all directions. So this is the p representation. This is the Wigner function. And what about the Husini distribution? What is it going to look like? Well, it's going to, again, be centered at the same thing, but it's going to have more noise. It's going to be more smeared out. It's a coarser version of the Wigner function. Okay? And it does not capture everything there is to capture. Yes, sir?
All the information's still there though, right? If we do some math, we can...
It is. All the information is still there. It's a question of how we interpret what these distributions mean. In the same spirit, as we said, as you know from your elementary quantum mechanics, when you think about wave mechanics, you could talk about the position space wave function or the momentum space wave function. They're both different representations of the same state. But those different representations have interpretations in terms of measurements. If I measure momentum, then the square of the momentum space wave function tells me something about the probability of that measurement. It's buried in the x representation, but not in its simple way. Okay? And that's a similar story here. If I'm doing a homodyne measurement, it is the Wigner function that tells me about the probability distribution of seeing certain homodyne measurements. If I'm doing direct photon counting, it's the p distribution. If I'm doing heterodyne, it's the q function. So they're all buried in there. They have different they have different implications for measurement. Okay. Excellent. So I want to say just one last thing about this topic before we move on. And that is the question of negativity as a resource. Now, negativity can drag us down sometimes, but negativity can be a resource if you know how to harness it the right way. So I want to come back to something we talked just very briefly about when we were, I don't know what we were motivating at the time. We were motivating how you generate non-classical light. Let's talk just very briefly about this problem of boson sampling that we very briefly discussed, right? And the idea was that I had some kind of linear optical network. Let's say I had a bunch of modes coming in, bouncing off a mirror here. And in this case I have 3 modes in and 3 modes out, but I can have some number. I have some beam splitters, I have some phase shifters at each of these things. This is some big mirror, okay? And so I have input modes and output modes, right? And the boson sampling problem is the following. I have some probability of seeing some number of photons in each of the ends. So this is, say, n modes. Okay. And the goal is our goal in boson sampling is to create on the computer a random number generator which spits out random numbers according to this probability distribution, okay? Where these are the output probability distributions. Now, in a famous paper from 2011, Scott Aronson and his student showed that this actually, in principle, would be extremely hard, exponentially hard, or more, you couldn't do it with a classical computer if your input were single photon states. Okay? So suppose I put in individual indistinguishable photons into each of these modes. They're going to bounce around. Sometimes they'll come out like this, all 3 in that. That's some possible configuration. Okay? And I want to spit out random numbers with that probability. You can't do it efficiently classically. The amazing thing is that a linear optical network can do something that a classical computer could do. No quantum optician would have ever dreamed that was true, because linear optics is trivial. It's just trivial. Okay? So now I ask you the following question. Suppose instead of single photons here, I put in coherent states. Could you do it? Could you dream up a classical algorithm that would, if you wanted to just do photon counting at the output, could you come up with a classical algorithm that would do it? Ben's shaking his head yes. How would you do it?
You work in the P representation the whole time.
You can think about this. So we know in this case, the probability of seeing n photons, say in this one mode, what would it be? You'd be Gaussian. So let me ask you, before we get into this, let me ask you the following question. These are all my input. Okay, so my input state is, I have in each one of these modes, I have a coherent state. What's my output state?
Coherent state.
It's coherent states again, because a linear optical transformation takes coherent states to coherent states, right? And so, and how are these guys related to these guys? The scattering matrix, right? Or the transition matrix. We had that alpha I out was equal to the sum over the modes, and this is just the classical matrix that we would have with the transmission, and this is some matrix that tells me everything about the thing splitter. It's an n by n matrix, right? So it's efficient to calculate. So how, now, given that, I ask you the following question. What is this?
For a coherent state?
For each coherent state, what is the probability of seeing n
What do you mean?
photons? It's a Poisson distribution, right? This is just equal to the product, all the modes, everything is uncorrelated. So this is the product over all the modes. The probability of seeing n photons in that ith mode, which is that. Everyone agree? That's just the probability. I mean, that is what you said, and it is the p representation, but it's, you know, so that's one machination too far. Right? And that's a a Poisson distribution. Etc. So you just multiply that. You could do that sampling, right? You could do that efficiently. You could write a computer program that would just give you that easily. Okay? What if my state was a state which had a convex combination of coherent states for each mode, right? Could you do it in that case? Sure, you would just do this, and then you'd have to sample over. You'd first do a Monte Carlo program that would pick out the right amplitudes out of this distribution, and then for each of those distributions, you would do a Poisson distribution, and that would be fine. It would work. It wouldn't take that long, okay? But what if I put in squeeze states into each of these modes? Well, if I have a squeeze state, as you're seeing perhaps in your homework, it's no fun at all, but I asked you to do it. In that case, this thing is negative and highly singular for the squeeze states. Doesn't have a positive Glauber P representation. Okay? In that case, you couldn't do Monte Carlo sampling over this in that way. In fact, you couldn't, there's no way to do it. So, on the other hand, suppose that, so now I'm going to put in squeeze states here. Maybe we can even make them squeeze vacua. And instead of doing direct photon detection, I'm going to do homodyne on each of these output modes. And I wanted, instead of simulating the probability distribution of numbers, I'm going to ask what is the probability of seeing a certain quadrature value in each of the output modes. Could you do that classically? So the idea is, instead of asking what's the distribution of photon counts, I'm asking what's the distribution of quadrature measurements.
Seems like you should be able to, since squeeze states look classical.
Exactly, because everything is Gaussian, and this is all positive here, right? It's the linear transformation here will take a Gaussian state into a Gaussian state. And then the output probability distribution I just sample from Monte Carlo. So, one of the morals of the stories here, there's two morals of the story here. One is negativity is a resource. For complexity. For boson sampling, if I'm going to use photon counting, what's required is that the P function be negative. If I have non-classical light in the Glauber sense, then putting it through this linear optical network can generate complexity that I could not simulate efficiently classically. Okay? On the other hand, I have to be careful about what I'm measuring, because a squeeze state has a negative P representation, and thus complexity with respect to direct photon counting. But it's not complex with respect to homodyne detection. That was perfectly classical in that sense. And this has been a subject of modern exploration research, and I want to show you just a couple of papers. I guess I can turn on here that show what is being done today in this area.
The very last one. No.
All right, here is a paper from none other than Professor Caves, Professor Emeritus Caves, when a few years back with, damn you, Mac OS. When he was working with some students and others in Australia, Saleh Shari, and what they were looking at this question of boson sampling and asking about the following question, really, how do, what I just described to you in the context of boson sampling is the idea of a noiseless system. As you know, anyone who's worked in a lab knows that photons will be absorbed in your optics. And you're not going to align this thing perfectly. And you're going to have dark counts in your detectors. And these are not actually identical photons. They're slightly misaligned. So all of that, we can ask your question, at what point is there, due to these losses, is there so much noise in some sense that the system becomes classical? And I should be able to find a classical summation. And what they looked at it is in terms of phase-based quasi-probability distributions. And they looked at the question of whether or not there was negativity with respect to some ordering, any ordering, the continuum of orderings. That's your question about, is it useful to think about the parameter sigma as a continuous variable that goes from -1 to +1? And they asked if there is negativity, or if all of these things, if for some ordering, the input state, the measurements, and the transition function, because all of those things are operators, and you can write down a quasi-probability distribution, or a PBQ, whatever they're calling PQD, for any of them, and they went through that analysis using exactly the things that we have just been talking about. Here's they use S rather than sigma, the S-ordered representations, that's the characteristic function with this Gaussian thing. And they said if there is some S for which everything is positive, then we can come up with a constructive algorithm to sample these things. There's a measurement, and I can do it classically. And there's a kind of threshold of noise for which that happens. A really fascinating piece of work, I think. I wanted to show you one other recent piece of work in the last few years that I think is very exciting on this front also. So we've talked here about the representations in phase space in infinite dimensions, right? So for something like a harmonic oscillator or a mode. But you can do that as well for other dimensional Hilbert spaces, including finite dimensional Hilbert spaces. And in this work, they asked the following question. If I want to do a quantum computation, what is the secret sauce that makes it go beyond classical statistics? And they showed this remarkable connection between the potential for quantum speedup and the onset of negative values in quasi-probability representations. Chris Ferry was a postdoc here at UNM, so we're always proud to point out our UNM connections here. So I'll send you guys his papers in an email, and you can look at them yourself. But I think it's one of these things that in modern times we're really beginning to understand that this, negativity in the quasi-probability representations is not just an oddity, but it's a resource in the same way that we've come to understand, as we're going to talk about in our next object of entanglement as a resource for information processing, not just something that is a surprising aspect that distinguishes it from classical dynamics. All right, excellent. All right, very good. I guess it's something here. All right. So now I want to turn our attention to the question of entanglement. So, for the most part, what we have been talking about this semester and for the most of the last, when we've been talking about non-classicality in quantum optics, we've been talking about So we've just talked about negativity, for example, as a resource. Now, things become, if we start thinking about multimode, then of course there's a whole other set of very interesting features, and in particular, the whole question of entanglement. And so, entanglement is going to be the star of our show for the remainder of the semester, really, in very many ways. Entanglement, as you know, is one of the most fascinating features in quantum mechanics. As I said, we think about it also as a resource, but it also has very important notions from the foundations in ideas related to open quantum systems and measurement, which are all going to be the topics of the remaining parts of the semester. Okay? So I'm going to go through some things fairly quickly for the remainder of this lecture, just to remind ourselves about some notation and formalism that I'm sure the vast majority of you are familiar with, but I think it's important to go through it from the beginning. Okay? So let's just think about, so a single mode I think about as 1 degree of freedom. And multi-modes I think about as multiple degrees of freedom. So in thinking about a degree of freedom, let's go back to the most basic thing. Let's think about 1 degree of freedom. Particle on a line. It has a position and typically a momentum, and that's how we would think about it in classical phase space, right? I can write, for example, I can think about the probability distribution in X or in P, or I can think about a Wigner function if I want to think about it in X and P at the same time. Think about, say, 2 degrees of freedom. Think about 2 particles on a line. Now, of course, I can write down the wave function for, say, where the 2 particles are in X, and I can write down a probability distribution, probability density, okay. And I can think about marginals. So if I wanted to know what is the probability distribution to find particle 1 at position x1, irrespective of where particle 2 is, I marginalize the distribution, or vice versa. Now, if my state was separable, so I have a pure state. So let's call this just for let's say there's particle A and there's particle B. I could have a wave function for particle A and a wave function for particle B. Then, of course, the joint distribution is just the product distribution. which are equal to the marginals in this particular case. So if the product state, if I had a pure state, and if it was a product state, which we call separable, then the marginals are just the squares of the wave function, one associated to particle A and another associated to particle B. Okay. On the other hand, suppose that I have the following pure state for my two particles. So let's say my wave function for my two particles was this, where these were, say, harmonic oscillator ground and first excited state. Okay. Let's just say we had that state with some complex coefficients alpha and beta. Perfectly good state. So now I ask you the following question. What is the marginal of finding, say, particle A at position 1, irrespective of where particle 2 is, or particle B? How would you calculate this thing? Well, we do that. We make the square of the wave function, and we marginalize it. That's the joint probability distribution. And if we marginalize it over 2, we average over all the 2's, we get this. So what is that? You have to square that, and then do the average. So I'm going to get the square of this term. Average over 2, that's normalized. So I'm going to get alpha squared that. And then I get the square of that term. And when I marginalize, that's normalized. And then I'm going to get the cross term, right? I'm going to get this starred with that. And I'm going to integrate that over 2. And what am I going to get? When I have this star with that, and I integrate over 2. These are the inner product of that, which is 0, right? Because these guys are orthogonal. So that's the answer. This is a statistical combination of these two probability distributions. Right? This is what is sometimes called a convex combination. It's a heavy-handed word. But it's a statistical mixture of this and this. Right? And similarly, if I were to marginalize, I don't mean to marginalize anybody, but I'm going to marginalize this distribution. The probability distribution for finding particle B at 2, irrespective of what 1 is going to be this statistical mixture. I assign, I could not assign, you might, okay, let's finish the sentence. Can I assign a wave function to particle 1 and a wave function to particle 2 such that the joint wave function is this? You might think, well, okay, if this is the probability distribution, I'm going to define the wave function up to some phase as the square root of this. That seems like a fine thing to do, so that when I square it, you know, I might put a phase in there. I don't know what that phase is, but maybe I don't care. So I'm going to call this the wave function. I might think that's a reasonable thing to do. And then take some other, make that the wave function. But that isn't the wave function for particle 1 or particle 2. What is the wave function for particle 1 or particle 2?
Top one.
Well, the top one's the joint wave function of both particle 1 and particle 2 together. That's their joint wave function. But what wave function do I assign that tells me about measurement outcomes on particle A? Because we said, you know, the wave function is a vehicle for calculating the probabilities of measurement outcomes. That's what the wave function is. So what wave function should I assign to particle A?
The margin waves.
That's not a wave function.
That's
It's a probability distribution.
assign it a mixed state.
So what this thing is, there is no wave function I can assign to it. In fact, as we will see, what I have to assign to each one of these guys is a density operator. Even though the joint state is a pure state, the marginals are mixed. Now, I love doing this because usually this is never introduced in terms of wave mechanics, but it should be. It's not just about matrices and some it's just, you could just see this in terms of you cannot, if I had a positronium atom and it was a electron and a minus electron and they went apart from one another, there is no wave function I can define to measurements on the electron or the positron. I can define the joint wave function. But this is a mixed state, as we will see. There is no wave function associated with the marginals. And this is one of the most amazing things. This state is an entangled state. And that's one of the hallmarks of entanglement, as we will remind ourselves. Yeah?
So this is basically the EPR argument, right?
Well, I mean, you know, EPR, of course, employed entanglement to make their argument, but their argument was about causality and so forth. We'll get to that.
So
Yes, I'm listening.
my question is, why did they take it for granted that this state should exist? Why was not? I mean, if I saw this in 1920s, I would say maybe this state wouldn't be possible to create. Why was that never? Is it obvious that this state should be possible to make or like exist?
You know, I can't go into a time machine and to know what they were thinking and what, but my guess is, you know, as theoretical physicists are wont to do, the idea is to push the theory to its boundaries. So it's not a question of whether the laboratory, whether one could create such a system in the laboratory, it's the formalism allows this. What are the implications of that formalism? As we will remind ourselves or learn if we haven't seen before, EPR is about a particular kind of entanglement, the original EPR, which was in the 1930s. And that particular state is actually wasn't so easy to make, and actually has its own issues relative to the EPR, relative to the whole question of local hidden variables, as we will see. And David Bohm came along in the 1950s and revisited EPR and said, instead of thinking about X and P, which is what was the want in the day, David Bohm said, let's think about spin singlets. So the issue of how do we actually produce entangled states came up later. In the 1930s, it was more, Gedanken. Yeah.
Isn't this a fairly easy state to make? Like you could do a pi house pulse.
Sure. Yeah, it is easy. But, back in the day, I think Picasso's point is that might not have been obvious. You have coherent control. People didn't do those kinds of things in the 1930s.
Yeah, but they knew about like a pi house pulse for NMR, right?
Sure. This is, to you guys now, this is, boy, just put on a pulse and it worked. But, of course, the real hard part in the laboratory of any of this is about this part. That's the hardest thing to get to. So the idea of how you get to something that is effectively at zero temperature, right? So, if I thought about this as, two particles in a well, I have to have, one particle in the ground state and one particle in the first excited state, and then I don't know which one it is. But I have to cool them to the ground state, right? And, people are doing this in all kinds of systems now, right? I mean, of course, Dave Weinland won the Nobel Prize for his ability to control individual quantum systems, the development of laser cooling techniques to cool the motion of trapped ions near to the ground state was revolutionary in the 1970s, 80s, and then moving into the 90s and beyond. More recently, people are looking at things like nanomechanical, membranes, and the ability to take what we might think as macroscopic systems and bring them to near zero entropy has been a experimental and technological feat. We can think about it, spin degrees of freedoms, etc. Okay. Yeah, maybe I'll spend 5-10 minutes just reminding us of some basic notation. So, in thinking about entanglement, as we will see, it's much easier to think about in finite dimensions than in infinite dimensions. So instead of thinking about modes of harmonic oscillator or motion of a particle, we might think about spins, qubits or qubits for higher spins, all right? So let me quickly remind you of some notation and definitions. So an important idea here in thinking about multiple degrees of freedom is the tensor product in Hilbert space. So if I have 2 degrees of freedom, one I call A and the other B, there can be some Hilbert space associated with degree of freedom A, and another Hilbert space associated with degree of freedom B, and the joint Hilbert space, we say, is the tensor product of those. So this is a tensor product for 2 degrees of freedom. Okay? So we define formally if psi is a vector in Hilbert space A, and phi is a ket in Hilbert space V, then I can define a joint state in the state in the joint Hilbert space by the tensor product of these two. So this is just a formal product, which has properties that we'll remind ourselves of. Okay, so I can take any linear combination of those. So if it's a tensor product state, if I have, it's a tensor product Hilbert space if I can take the superposition of these guys. Say I have that's in the Hilbert space. Okay. So I take a superposition of these products, and that's in the space, then it's said to be a tensor product space. Now, just as a little aside, not all states, not all Hilbert spaces of multiple degrees of freedom are tensor product spaces. If I have identical particles, and I have a fixed number of identical particles, that's not a tensor product space because of the issue of exchange symmetry. Okay? So we have to, typically these are, we think about them as distinguishable degrees of freedom. Okay. And if I also have the inner product of two such states, let's call this psi 1, let's call this psi 2. Then the inner product between those two states is, by definition, I've used the inner product from Hilbert space A and I use the inner product from Hilbert space B. Okay, so these are complex numbers. I multiply them together to get the total inner product. Okay? That defines the tensor product Hilbert space. Okay. Now, importantly is the representation in a basis. So if I have a basis for Hilbert space A with some dimension. Could be infinity, but we'll be looking at finite dimensional ones for the most part. Not always. And I have some other basis for Hilbert space B. And those two Hilbert spaces need not be the same dimension. They could be different dimensional Hilbert spaces. Then we define the standard basis as a tensor product basis. And, oops. And what is the dimension of this space? The product of the two. So the total dimension of this Hilbert space is the product of those two dimensions. Okay. So if I have a product state, and if the representation in that basis, I'll call that alpha I, and the representation of state phi b and its basis I'll call beta j, then the representation in the standard basis of the joint state is equal to just the product of those coefficients. Okay. And we typically order them as such. We write this as a column vector, where we write the first index and then dot, 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 up to dimension b, and then 2, 1, dot, 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 and then eventually b, a, 1, dot, dot, dot. That's the standard order. So this, as a matrix operation, is the tensor product of these two column vectors. And when I do that, I put this is the way I always do it. Which is so that's the tensor product operation on the matrices. That is to say, the matrices that are the column vectors that define the two vectors. I take the tensor product and I get a big column which has a column vector which has dA times dB entries. And you see how I did it? I took this guy and threw it in here and multiplied all those guys together. This guy, and that is the standard ordering of the tensor product. Okay? And finally, just to remind you about operators, so I can have an operator that might be itself a tensor product of operator where this operator acts on Hilbert space A and this operator acts on Hilbert space B, right? And by definition, if I act this tensor product operator on some state, and if that state itself is a tensor product state, then I obtain that by acting A on the first state and tensor producting that with B on the state phi in Hilbert space B. And with that, we can look at matrix representations, right? So the matrix representation, for example, let's say I have 2 qubits. And let's look at the matrix, oh, I don't know, sigma x tensor to sigma z. Okay. In the standard basis, the spin up and down along z basis, sigma x is that, and and sigma z is that. So how do I take that tensor product? In the same way, I shove this guy in here. This is 0 times that. And 1 times that. And 1 times that. And 0 times that. You see what I did? If you're not familiar, I shoved this in to each element. That's how I take the tensor product. Maybe you don't do it that way, but that's how I do it. So this is 0, 0, 0, 0, 1, 0, 0, minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0. Okay. All right. Just to get us all on the same page. All right. So we will continue our discussion of multi-partite systems, particularly bipartite systems, and thinking about this whole question that we saw here of this relation between entangled states and more harmonic states. Very good.